EET 105, inductors 1126. Find, it says for this network, first of all, the switch is closed at t equals 0. Determine VL at t equals 25 microseconds. So what we're going to do is find the Thevenin circuit for the inductor. So at A and B is this point right here. With this switch closed and this shorted, this is the Thevenin equivalent to find a resistance. It's R1 in parallel with R2 plus R3, and all of that in parallel with R4, which is 0.816 kiloohms. So then the E Thevenin would be putting the source back in, finding the RT, which would be R1, R3 and R4 in series. Those are in parallel with R2 as shown here, and then that's in series with R1, so RT is equal to 9.58 kiloohms. IS equals E divided by R, they're calling it RT prime. 36 divided by 9.58 kiloohms, 3.76 milliamps. And then I prime is the current going through this leg. So we need our old buddy, the current divider. IS is coming in. And then I prime is going through R4 and R3 right as shown here. So it would be R2, which is the other leg, times IS all over R2 plus R3 plus R4 equals 1.4 milliamps. And finally, E Thevenin is the voltage across this resistor, which is I prime times R4, which is 1.4 milliamps times 1K equals 1.4 volts. Tau, then, this is the Thevenin equivalent. E Thevenin in series with R Thevenin, with the inductor as the load, VL. Tau is equal to L over R, that's 10 millihenries divided by 0.816 kiloohms, 12.25 microseconds. So for the storage voltage, this is the formula. The 1.4 V times E to the minus T divided by 12.25 microseconds. The problem asked us put in T equals to 25 microseconds. So when you put that in for small t, you do the math, you get 1.4 e to the minus 2.05 power, and then that equals 180 millivolts. Then it says find VL at t equals 1 microsecond. So you use the same formula. You put in t is 1 microsecond, 1.4 times e to the minus 1 microsecond divided by 12.25 microseconds. Do the math, and you get 1.29 volts. Part C says calculate VR1 at t equals 1 time constant, 1 tau. So what they did was they redrew the circuit like this and find the Thevenin equivalent for R1 at 1 tau. So what they did was they put in V sub L at 1 tau. They calculated it same way we just did it down here using this formula. So 1.4 times e to the minus t over tau. You put in t equals 1 tau, tau equals tau, so 1.4 times e to the negative 1 equals 515.2 millivolts. So they put that back in there, and then R1 is the load now. So they redrew the circuit like that. And then calculating R Thevenin with this shorted, this is where the load is, AB. It's just these two resistors in parallel. This is also shorted, 1.21 kiloohms. Then E Thevenin at that point, put the voltage source back in, this voltage source back in, going around this loop, we have minus E Thevenin plus 36 minus VR2, which is across the 2.2K resistor. So you can calculate VR2 is a voltage divider. Well, they wrote this equation first. E Thevenin equals 36 minus VR2. Then VR2 is also a voltage divider. This is VR2 right here. They just didn't draw it across the circuit. So it's a voltage divider because it's in parallel with this voltage. And so they took 2.2 times this voltage here divided by these two voltages equals 0.231 volts. So now you know what VR2 is. You can calculate E Thevenin prime. 36 minus 0.231 equals 35.77. So then what they did was they took E Thevenin and put in R1 back in the circuit and then have R Thevenin in series with it. It's the same thing that we've been doing. They just kind of flipped it around and it's going in this direction instead of that direction, but it doesn't matter. And then they did another voltage divider, so 8.2 times 3.5, 35.77 divided by 8.2K plus 1.21 equals 31.34 volts. So then the last question is find the time required for the current IL to reach 1 milliamp. So during the storage phase, this is the formula. Only we're using E Thevenin and R Thevenin instead of just E over R. We already figured out what E Thevenin is over here, and what R Thevenin was. Where was it? Over here, right there, 8.816. So plugging those numbers back in, and then solving for IL, given that it was 1.1 milliamp in the problem, all you have to do is find little t, and the way to do that is to simplify it down to this, then to this, then to this, and then you take the natural log of both sides, and what you get is minus t divided by 12.25 microseconds equals ln of 0.419, which is what they did here, and then it ends up equaling 10.66 microseconds.